Alright, welcome to part 4 of the ARP scaling video. I'm going to finish reading up this RFC. Feeling pretty tired already, but I think a half an hour video will be plenty if that's all I can do. So as soon as I'm finished with ARP scaling, the next topic will be reading the BGP RFCs, but I'm going to need to finish this first. So where I left off last time was factors that affect data center design. So the first factor is traffic patterns. Expected traffic patterns play an important role in designing appropriately sized access, aggregation, and core networks. Okay, so and let's look back at these notes here I've got. So one of the questions we're going to be asking ourselves, this is my series on wild networking. You're more concerned with what you're going to see on the job or out in the wild as opposed to what's on a test. So out on the job, you're going to hear a question, why is my internet so slow? You won't necessarily hear that on the job, but if somebody hears that you're a network engineer, I've already gotten asked this many times by people just casually in conversation or just at non-workplace professional events. So this is the question we'll be having in mind as we go forward. Why is my internet so slow? The second question will be how do I design my network? So there's a whole track that you can do for design. That would be a good answer for this, but it's regardless of whether or not you have a cert, it's an important real world question to be asked, especially on the job. So we've got so let's keep track of this. So one of the things you've got to consider, or what do I need to consider when designing my network? There we go. So you need to consider traffic patterns. You need to consider virtualization. Yep. You also need to consider trade-offs and limitations, such as having a special device on your access layer that requires layer 2, a single flat broadcast domain. There are devices that require that. And so those are our 3 things. Let's continue to read the RFC. Expected traffic patterns play an important role in designing appropriately sized access aggregation and core networks. Traffic patterns also vary based on the expected use of the data center. Broadly speaking, it is desirable to keep as much traffic as possible on the access layer in order to minimize the bandwidth usage at the aggregation layer. If the expected use of the data center is to serve as large a web traffic server farm, is to serve as a large web server farm where thousands of nodes are doing similar things and the traffic pattern is largely in and out of a large data center, an access layer with end-of-rack switches might be useful, as it minimizes complexity and allows for servers and databases to be located in the same layer 2 domain and provides for maximum density. A data center that is expected to host a multi-tenant cloud hosting service might have some complexity, some completely unique requirements. In order to isolate inter-customer traffic, smaller L2 domains might be preferred, and though the size of the overall data center might be comparable to the previous example, the multi-tenant nature of the cloud hosting application requires a smaller and more compartmentalized access layer. A multi-tenant environment might also require the use of layer 3 all the way to the access layer TOR switch. Yet another example of a workload with a unique traffic pattern is a high-performance compute cluster, where most of the traffic is expected to stay within the cluster, but at the same time there is a high degree of crosstalk between the nodes. This would once again call for a large access layer in order to minimize the requirements at the aggregation layer. Virtualization. Using virtualization in the data center further serves to increase the possible densities that can be achieved. However, virtualization also complicates the requirements on the access layer, as virtualization restricts the scope of server placement in the event of server failover, resulting from hardware failures or server migration for load balancing or other reasons. Virtualization also can place additional requirements on the aggregation switches in terms of address, resolution, table size, and the scalability of any address learning protocols that might be used on those switches. The use of virtualization often also requires the use of additional VLANs for high availability beaconing, which would need to span the entire virtualized infrastructure. This would require the access layer to also span the entire virtualized infrastructure. Summary. The designs described in this section have a number of trade-offs. The L3 to access switches design described in section 6.4.1 is the only design that constrains L2 domain size in a fashion that avoids ARP/ND scaling problems. However, that design has limitations and does not address some of the other requirements that lead to configurations that make use of larger L2 domains. Consequently, ARP/ND scaling issues are a real problem in practice. Problem itemization. This section articulates some specific problems or pain points that are related to large data centers. ARP processing on routers. One pain point with large L2 broadcast domains is that routers connected to the L2 domain may need to process a significant amount of ARP traffic in some cases. In particular, environments where the aggregate level of ARP traffic is very large may lead to a heavy ARP load on routers. Even though the vast majority of ARP traffic may not be aimed at that router, the router still has to process enough of the ARP request to determine whether it can be safely ignored. The ARP algorithm specifies that a recipient must update its ARP cache if it receives an ARP query from a source for which it has an entry. ARP processing in routers is commonly handled in a slow path software processor rather than directly by a hardware application-specific integrated circuit, ASIC, as is the case when forwarding packets. Such a design significantly limits the rate at which ARP traffic can be processed compared to the rate at which ASICs can forward traffic. Current implementations at the time of this writing can support ARP processing in the low thousands of ARP packets per second. In some deployments, limitations on the rate of ARP processing have been cited as being a problem. To further reduce the ARP load, some routers have implemented additional optimizations in their forwarding ASIC paths. For example, some routers can be configured to discard ARP requests for target addresses other than those assigned to the router. That way, the router's software processor only receives ARP requests for addresses it owns and must respond to. This can significantly reduce the number of ARP requests that must be processed by the router. Another optimization concerns reducing the number of ARP queries targeted at routers, whether for address resolution or to validate existing cache entries. Some routers can be configured to broadcast periodic gratuitous ARPs. Upon receipt of a gratuitous ARP, implementations mark the associated entry as fresh, resetting the aging timer to its maximum setting, consequently sending out periodic gratuitous ARPs can effectively prevent nodes from needing to send ARP requests intended to revalidate stale entries for a router. The net result is an overall reduction in the number of ARP queries routers receive. Gratuitous ARPs broadcast to all nodes in the L2 broadcast domain may in some cases also pre-populate ARP caches on neighboring devices, further reducing ARP traffic, but it is not believed that pre-population of ARP entries is supported by most implementations, as the ARP specification RFC 826 recommends that only pre-existing ARP entries be updated upon receipt of the ARP messages. It does not call for the creation of new entries when none already exist. Finally, another area concerns the overhead of processing IP packets for which no ARP entry exists. Existing standards specify that one or more IP packets for which no ARP entries exist should be queried pending successful completion of the address resolution process. Once an ARP query has been resolved, any queued packets can be forwarded on. Again, the processing of such packets is handled in a slow path, effectively limiting the rate at which a router can process ARP cache misses, and is viewed as a problem in some deployments today. Additionally, if no response is received, the router may send the ARP/ND query multiple times. If no response is received after a number of ARP/ND requests, the router needs to drop any queried data packets and may send an ICMP destination unreachable message as well. The entire process can be CPU intensive. Although address resolution traffic remains local to one L2 network, some data center designs terminate L2 domains at individual aggregation switches/routers. Such routers can be connected to a large number of interfaces, for example 100 or more. While the address resolution traffic on any one interface may be manageable, the aggregate address resolution traffic across all interfaces can be problematic. Another variant of the above issue has individual routers servicing a relatively small number of interfaces, with the individual interfaces themselves serving very large subnets. Once again, it is the aggregate quantity of ARP traffic seen across all the router's interfaces that can be problematic. This pain point is essentially the same as the one discussed above, the only difference being whether a given number of hosts are spread across a few large IP subnets or many smaller ones. When hosts in two different subnets under the same L2/L3 boundary router need to communicate with each other, the L2/L3 router not only has to invalidate ARP/ND requests to the target subnet, it also has to process the ARP/ND requests from the originating subnet. This process further adds to the overall ARP processing load. Okay, I'm almost done. I'm really feeling it, but I think I can continue because I'm so close. IPv6 neighbor discovery. Although IPv6's neighbor discovery behaves much like ARP, there are several noticeable differences that result in a different set of potential issues. From an L2 perspective, an important difference is that ND address resolution requests are sent via multicast, which results in ND queries only being processed by the nodes for which they are intended. Compared with broadcast ARPs, this reduces the total number of neighbor discovery packets that an implementation will receive. Another key difference concerns revalidating stale ND entries. ND requires that nodes periodically reevaluate any entries they are using to ensure that bad entries are timed out quickly enough that TCP does not terminate a connection. Consequently, some implementations will send out probe ND queries to validate in-use ND entries as frequently as every 35 seconds. Such probes are sent via unicast, unlike the case of ARP. However, on larger networks, such probes can result in routers receiving many such queries. For example, many more than with ARP, which does not specify such behavior. Unfortunately, the IPv4 mitigation technique of sending gratuitous ARPs as described in section 7.1 does not work in IPv6. The NT specification specifically states that gratuitous ND updates cannot cause an ND entry to be marked valid. Rather, such entries are marked probe, which causes the receiving node to eventually generate a probe back to the sender, which in this case is precisely the behavior that the router is trying to prevent. Routers implementing neighbor unreachability discovery NUD for neighboring destinations will need to process neighbor cache state changes, such as transitioning entries from reachable to stale. How this capability is implemented may impact the scalability of network discovery on a router. For example, one possible implementation is to have the forwarding operation detect when a neighbor discovery entry is referenced that needs to transition from reachable to stale by signaling an event that would need to be processed by the software processor. Such an implementation could increase the load on the service processor in much the same way that high rates of ARP requests have led to problems on some routers. It should be noted that the neighbor discovery does not require the sending of probes in all cases. Section 7.3.1 of RFC 4861 describes a technique whereby hints from TCP can be used to verify that an existing neighbor discovery entry is working fine and does not need to be re-evaluated or revalidated. Finally, IPv6 and IPv4 are often run simultaneously and in parallel on the same network, i.e. in dual stack mode. In such environments, the IPv6 and IPv4 issues enumerated above compound each other. MAC address table size limitations in switches. L2 switches maintain L2 MAC address forwarding tables for all sources and destinations traversing the switch. These tables are populated through learning and are used to forward L2 frames to their correct destination. The larger the L2 domain, the larger the tables have to be, while in theory a switch only needs to keep track of addresses it is actively using, sometimes called conversational learning. Switches flood broadcast frames, for example from ARP, multicast frames, for example from neighbor discovery, and unicast frames to unknown destinations. Switches add entries for the source addresses of such flooded frames to the forwarding tables. Consequently, MAC address table size can become a problem as the size of the L2 domain increases. The table size problem is made worse with VMs, where a single physical machine now hosts many VMs in the tens today, but growing rapidly as the number of cores per CPU increases, since each VM has its own MAC address that is visible to switches. So this document has, when L3 extends all the way to the access layer, see section 6.4.1, the size of MAC address tables and switches is not generally a problem. When L3 extends only to aggregation switches, see section 6.4.2. However, MAC table limitations can be a real issue. Summary: this document has outlined a number of issues related to address resolution in large data centers. In particular, this document has described different scenarios where such issues might arise and what these potential issues are, along with outlining fundamental factors that cause them. It is hoped that describing specific pain points will facilitate a discussion as to whether they should be addressed and how best to address them. Yeah, okay, there's some security considerations in other documents. I kind of want to read this on ARP because it looks pretty short. Yeah, it looks short. It's an internet standard. This looks pretty good as well. I think this is going to be it for this. Yeah, I think this is going to be it for this video. Though I'm getting really tired, and I'm running out of energy to continue. So yeah, that's going to be the end of this video. I'm now completely finished, I think, with ARP scaling. So the next is going to be BGP. Thanks for